Another famous ensemble method is random forest. So ensemble method in general consists of multiple weak classifiers, and in random forest we use decision tree as the weak classifier. And this slide shows what the decision tree look like. So let's say we have an input data like this. These are input attribute, and this is the target attribute. Then using this data, we can construct a decision tree which look like this. So in random forest, it consists of multiple of these decision trees. Even though the decision tree is one of the classical machine learning algorithm, it has its own set of limitations. The first problem is actually the performance of decision tree is not as competitive as other more advanced algorithms. So its prediction accuracy is actually quite low compared to other learning methods. Second problem is related to data fragmentations. So in data fragmentation, what happens is, so when we add more node in decision tree, then okay, when you reach near the bottom of a decision tree, the attribute selection is actually based on less and less data. Okay, then this actually makes your attribute selection process more unreliable. Okay, so that is a problem. So because of that, the decision tree sometimes suffers from overfitting or underfitting. So in overfitting, we already covered this in the chapter of decision tree. So when your decision tree is too complex or it has too many nodes, then it suffers from overfitting problem. And the opposite is if your decision tree is too simple, actually it suffers from underfitting. Okay, so it may suffer from underfitting or overfitting. So that's the second problem of decision tree. So the problem of decision tree is related to stability. And decision tree is actually very sensitive to details of training data. What it means is if you change just a single or just a few data in training data, then sometimes it may end up generating a completely different decision tree. Okay, so this means the decision tree has very high variance. Okay, and it usually end up degrading the performance of decision tree. So the random forest is an ensemble method, and it consists of unpruned decision tree, and each decision tree is created by using a bagging method. So that's basic structure of random forest. So random forest is an ensemble consists of bagging of unpruned decision tree. So this was proposed by Bryman in 2001. So random forest is an ensemble method, okay, using decision tree classifiers, and it grows many classification decision trees. And again, in random forest, we use unpruned decision tree. In ordinary decision tree, it has two steps. The first step is to construct the decision tree, and the second step is actually pruning the decision tree, right? But in random forest, we do not prune the decision tree. So we actually generate decision tree in full scale, and we do not prune. Okay, so that's the decision tree you're gonna use in random forest. So after we generate many decision trees, each decision tree make predictions, and at the end, this random forest choose the classification which has the most vote. Okay, this is the final classification value of random forest. And each decision tree in random forest is actually generated by using bagging technique. So we have seen the bagging method in earlier. In random forest, it uses bagging method, but the bagging method we use in random forest is a little modified version of bagging technique. So we're gonna talk about this later, okay? But anyway, this random forest uses a substantial modification of bagging technique. So by using this modified version of bagging technique, it generates many decision trees. Okay, again, it is unpruned decision tree. So it builds a large collection of decorrelated trees. So decorrelated means independent. Okay, so it generates a large collection of independent decision trees. Okay, that is the key. Independent is very important. Okay, and then after that, at the end, we average these decision trees. Okay, that's the basic skeleton structure of random forest. This shows the classification boundaries generated from a single decision tree and also from a random forest, which is an ensemble of decision tree. So in this example, suppose this diagonal line is the optimal correct boundary which separates between red and blue. So, but in a single decision tree, in this case, card or it doesn't matter, okay, as card, this light orange color is the boundary generated by decision tree, okay, and it looked like this, and this is not, this is too naive, and it is not sophisticated enough, okay. But if you use a random forest, okay, which is a collection of decision tree, and this dark orange, this one here, shows the boundary generated from a random forest, which is more sophisticated, okay. So this shows the difference between the boundary of classification boundary of the single decision tree and the classification boundary of a random forest. In this case, suppose this one here, this circle is the optimal, the correct boundary between red and blue. Okay, so the goal is to draw a boundary like this. Okay. If you use a single decision tree, and it may draw something like this. Okay, again, this is not very promising. Okay, it's too naive. Okay. But if you use 100 bagged trees in random forest, this is the shape of classification boundary from random forest, which is more accurate, right, than this one. So this this picture shows the advantage of using ensemble method random forest compared to a single decision tree. This picture shows the entire structure of random forest. So let's say we have original training data, and then by using bagging method, we create random samples, let's say of 10 of them, okay? So these are randomly selected sample from original data. Okay, we have 10 of them, and for each sample data here, we generate a decision tree like this. Okay, and again, we use unpruned decision tree. Okay, we do not prune any of these decision trees. And another thing is when you generate the decision tree, we do not use entire attribute of data here. We randomly select a subset of attribute in the data. Okay, that's how we generate decision tree. So by using bagging, we randomly select subset of data here. And when you generate decision tree, we randomly select a subset of attribute here. Okay, that's how it works in random forest. So, and then each decision tree make predictions here, and finally these decisions are combined into one final classification value. So that is how this random forest works. This one is an example of combining the result from different decision trees in random forest. Suppose we have three different decision trees, tree 1, tree 2, and three decision tree 3. And also we have new data whose values are old, retired, male, and short. So the goal is to classify this new data, okay, whether it is disease or healthy. So by using decision tree 1, its value is old. You come here, and then its height is short, right? So its class value is diseased, right? So the prediction from decision tree 1 is diseased, right here, okay? By using decision tree 2, it is old, so it comes here, and its gender is male, so it's male, so it is healthy. So the prediction from decision tree 2 is healthy. From decision tree 3, it is retired, so it comes here, and its height is short. Short comes here, so it's diseased. So the prediction from 3 is diseased. So we have diseased, healthy, and diseased. So by using a majority vote, the final answer is diseased. So that's how we combine the result from different decision trees. Random forest has some advantages over some other machine learning method. The first one is random forest is actually the one of the state-of-the-art method and used in many applications. So the algorithm is quite competitive with many other advanced algorithms. And this algorithm is fast both in the training and testing. That's another advantage. And this method is quite easy to implement. And another advantage is you can run this in a distributed or parallel environment. And this one is also inherently a multi-class classifier. Unlike SVM classifier, which is binary classifier, a random forest is a multi-class classifier, which is another advantage. And this one, random forest, also handles this noise of data quite efficiently. So these are some of the advantages of a random forest. In the beginning of Ensemble method, we have seen that one of the most important thing in Ensemble learning is to maintain the independency between weak learners. So in random forest, it introduces two sources of randomness to maintain its independency between decision trees. So it has bagging and random input vectors as a tool for randomness. So in bagging, so actually each decision tree is constructed using a bootstrap sample of training data. So in bootstrap, we randomly select sample with replacement from original data. So this is called bagging method. and this is the first source of randomness in random forest. Second randomness is called random input vectors. So when you construct a decision tree, you select a best attribute for the node, but in random forest, you do not choose an attribute out of entire attribute, okay? You select a subset of attribute from original attribute, and then your best attribute is selected from that subset of attribute, okay? That's how you choose as best attribute in decision tree of random forest. So this subset of attribute is called random input vectors. So in bagging, you randomly choose data from original data or from original training data. So in random input vectors, you randomly choose attribute from original data. Okay, so we have two different kind of randomness in random forest. So by using this, random forest shows good accuracy without worrying about overfitting problem. And this random forest is quite fast algorithm, and sometimes it's even faster than growing and proving a single decision tree. Okay, and then this random forest can be easily parallelized. So in other words, you can construct a decision tree in a parallel manner, and it can handle high dimensional data without much problems. Because when you construct decision tree, the best attribute is chosen from a sample, okay, a subset of attribute, not entire attribute, okay. So by doing so, we are able to handle a high dimensional data, okay. And the M is the size of a subset of attribute here. Okay, so M is the parameter of a random forest. So this M is a tuning parameter in random forest. So the small m, which is the size of attribute subset, is the only parameter in random forest. So suppose there are m input attribute in the original training data, then you randomly select small m attribute out of capital M, okay, and then your best attribute is selected out of this small m, okay, and this attribute is used as a node in your decision tree. Okay, that's how you select your best attribute in decision tree. So this small m, the value of small m is held constant during the forest growing. So once you determine the value of m in the beginning actually, and this value doesn't change, okay? So the number of attributes you choose from original actually is fixed throughout the process of decision tree growing. And each decision tree is grown to the largest extent possible. Okay, and so that means there is no pruning in each of decision tree. Finally, here the correlation between two decision trees increases. That means the error of random forest increases. So correlation between two decision trees increases means these two decision trees are dependent on each other, right? So in that case, it actually degrades the performance of random forest. Okay, again, this is very important issue, and the independence between these decision tree is very important in random forest, and also important in ensemble method in general. So how do we choose the value of small m in random forest? Actually, there is no final absolute answer for this value, but we do have some suggestions for the value of m. You can use random forest for regression as well as classification learning. So if you use random forest for regression learning, what you can do is each decision tree make prediction, and the average value of these predictions are the final output of random forest. So in this case, the suggested value for small m is the floor of capital M divided by 3. So this is a suggestion of the suggested value for small m for the case of regression. If you use a random forest for classification learning, again each decision tree make prediction, and the class value with the most vote is the winner. Okay, so in classification learning, suggested value for small m is the floor of square root of m. Okay, these are the suggested value of m for classification learning. So these are just suggestions. Okay, as I said, there is no absolute final answer for this. So in practice, this small m is a tuning parameter, and the optimal range of this small m is actually quite large. Okay, it's usually the range of m is quite wide. Okay, so it's one of the issue in random forest. The next topic we're gonna cover in random forest is called out of bag data, in short OOB data. So in random forest, we use bagging sampling method. So when you draw a bootstrap sample, which means bagging, some data will be selected in the sample, and the others won't be selected in the sample, right? So those data which were not selected in the sample is called out of bag data or OOB data. Okay. So in sample, we do sample in bagging. We do sampling. We do random sampling with replacement. Okay, so that means the probability of each data to be selected is given like this. Okay, so this is the probability of a single data to be selected in this sample. So n is the size of data. So if n goes infinite, this formula becomes this one, which is approximated to 63%. Okay, so that means on average, we 63% of data is selected in the sample, and the remaining 36% is not selected, which becomes out of bag data. Okay. So in random forest, we repeat this bagging method and generate a set of different samples, right? And using each of these samples, we construct different decision trees, right? So because of that, every decision tree we grow has different OOB samples, because each decision tree is based on different sampling training samples, right? So each decision tree has different OOB data. And also in original training data, okay, every data in original training data will be in bag for some trees. In bag means this particular data is used to construct this decision tree, and this data will be out of bag for some other decision trees. Out of bag means, again, this particular data is not used to construct the decision tree. So for every data in training data, okay, every record in training data, this data will be in bag for some decision tree, or it will be out of bag for other decision trees. Okay, so that's a definition of out of bag data. In machine learning method, the original data is divided into training data and the test data. And the training data is used to construct machine learning models like a decision tree. And the test data is used to evaluate the performance of machine learning model like, again, a decision tree. Here in random forest, the bootstrap sample, okay, which we use to construct decision tree, it is like training data in random forest, and the remaining out of bag data is like test data. Okay, so we use this bootstrap sample to build decision tree, and the remaining out of bag data is used to test the performance of decision tree or entire random forest. So as a result, to evaluate the performance of entire random forest, we're going to compute the error of out of bag data. So let's take a look. Each time we draw a bootstrap sample, we only use 63% of data, and the remaining 36, 37 becomes out of bag data. Okay, so we use the rest of observations or OB data as a test data. So let's say you pick one particular data xi, okay, and then this data xi may belong to in bag of a certain decision tree, or this xi may belong to out of bag data of decision trees, right? So so for every out of bag decision tree, it make predictions on data xi, okay, so that is denoted as here. So this means this is prediction on data xi by using decision tree B, okay, that's what it means here, okay. And the number of out of bag decision tree is about 37% of total number of decision trees. Okay, we have seen this here. And then so every out of bag decision tree make predictions on data xi. Okay, so we have multiple predictions for each of OOB decision tree, right? Then we compute the average of these predictions, and which is denoted as this. So this means this is a prediction on data xi using out of bag decision tree. Okay, so this is a prediction on data xi using out of bag decision tree here. So now we have predictions, average predictions, and now we can compute the error of this data. So this is true value minus the prediction value of on xi, right? So there are many variations of error. You can compute a squared error or absolute values. So whatever you choose, you can compute the error of this data. Okay, this is true value. This is the average prediction value by using OOB decision tree. So for every data you have error, right? Then you repeat this for every data, okay? So all this error for every data is now combined, and you compute average of the total error, okay? So that is the final estimate of OOV error for random forest, okay? This is an example of computing out-of-bag error. Suppose this is the original data, and by using bagging, we do random sampling with replacement. So suppose this is the sample by using bagging. So we select 3 data and make sure this data is selected twice. Okay, so in bagging, we do random sampling with replacement. That means some data may appear multiple times, and some other data may not appear in the sample. So let's say this is the bootstrap sample by using bagging. And the remaining data, these 4, now becomes the out-of-bag data like this. We have these 4 out-of-bag data, okay? And I said bootstrap sample is kind of training data. This is kind of training data, and this is kind of test data. So by using this sample data, we construct a decision tree. So by using this, we construct a decision tree like this. Okay, and then let's compute the error of this out-of-bag data. So for each data in this out-of-bag data, you make prediction, okay, of this by using this decision tree. In this particular case, we assume there is only one decision tree, okay, but in general, there are multiple of decision trees. So by using this decision tree, you make predictions on each of these out-of-bag data. So all the 4, all total, its prediction is healthy, but correct answer is disease, right? So this is error, okay? For this one, young, short, young, healthy, the prediction is healthy. It's the same as the true value. Young, tall, young, prediction is healthy, and the answer is healthy. And old, short, prediction is disease, and the answer is disease. Okay, so for these 3, these are not error, and for this one, this is an error, right? So the error of this out-of-bag data is 1 out of 4, which is 0.25. Okay, this is the OOB error of these out-of-bag samples. Okay. Again, in general, we have multiple of decision tree, and we have many other out-of-bag samples. Okay, so for every out-of-bag samples, okay, we compute its error by using multiple of decision tree. Okay, so in this particular case, we have only one decision tree, and we have only one out-of-bag data. Okay. So the out-of-bag data can be considered as the test data of random forest algorithm. So therefore, the error of out-of-bag data is a very nice estimate of the performance of random forest. And one of the advantage of using this out-of-bag error is by using this out-of-bag error, we are able to determine the proper number of decision trees in random forest. So in random forest, we use many decision trees. Sometimes we have hundreds, or sometimes even we have thousands of decision trees. Okay, so how many decision tree we're gonna use is one issue in random forest. But by using this error of out of back data, we have very nice way of determining the proper size of decision trees in random forest. So if you look at this picture, so you keep increasing the number of decision trees. Okay, so in each step, this yellow line shows the OOB error, and this blue curve shows the real test error. And as you can see here, let's say from the point where number of decision tree is like 200 something. Actually, these two curves go in parallel, right? So from here, if you increase the number of decision trees from this point, like let's say number of decision tree is 200, actually it does make difference, right? The OOB error remains pretty much the same, okay, after the number of decision tree is, let's say, 200. Same thing in test error. If the number of decision tree is, let's say, 200, the test error actually doesn't change much. It's pretty much the same, right? So we can conclude the number of decision tree here can be around 200 something. Okay, after that, if you add more than 200, it doesn't make any big difference here. Okay, so by looking at this picture, you can conclude that in this case, the proper number of decision tree is around 200. This shows the structure of a random forest algorithm. Suppose n is the total number of decision tree you want to generate, then it repeats the following n times. So in the beginning, you take a random sample from the data with replacement, and this is called bagging. Okay. So as I said earlier, on average, 2/3 of data will be selected by the sampling, and the remaining 1/3 will be out of back data. And for each sample, we select a new random selection of data. Okay. So now we select a sample here. Then using this sample, you construct a decision tree. And when you build a decision tree in random forest, as I said many times, you build the tree to the maximum size, and you do not prune it. So in random forest, we do not prune decision tree. And another thing is, when you build a decision tree, you do not consider entire attribute, okay? You only consider a subset of total attribute when you choose a splitter attribute, okay? So when you construct decision tree, you have to choose an attribute, okay? So when you choose an attribute, you do not consider entire attribute, okay? You choose a subset of attribute first, and then you choose an attribute out of this subset. Okay, that's how it works. And then the second thing here is, so you select a subset for a particular node. Then for the next node, then you select another random subset of attribute. Okay, that is important actually. So for one particular node, you select a subset of attribute here, okay? And you select one node here, one attribute here, and it is added to the decision tree. Then in next step, you're going to add another node, right? In that case, you select another random subset of entire attribute, okay? So for every attribute, for every node, you choose different subset of attribute, okay? That is the key difference between building decision tree in random forest and regular ordinary decision tree. So after you construct n different decision trees, then each decision tree make predictions, okay, and then the final overall prediction can be average response in the case of regression, or majority voting for the case of classification. That these are the final answer of random forest learning. Another advantage of random forest is variable importance. There are many attributes in the data, and some attributes are more important than others. So the question is, can we somehow compute the importance of each attribute? So actually in random forest, it proposes a method called a variable importance to do that. So the basic idea of variable importance is the following. So you select a certain attribute, and then you change the values of the attribute, okay? And then if that modification decreases the accuracy of random forest, then we can say that attribute is important. That is the basic idea. On the other hand, if you change the values of certain attribute and the accuracies of random forest doesn't change, then we can say that attribute is not important at all. So this is the basic idea of variable importance. So we can compute the importance of each variable in random forest, and the variable importance is defined as the increase of error or decrease of accuracy after permutation of OOB data. So in the beginning, the accuracy of OOB data are computed for each tree. And as I said, the values of a particular attribute I are permuted in OOB sample. Permuted means you randomly change the values. And then after that, you compute the accuracy of permuted OOB data again, okay? Then probably the accuracy of permuted OOB is reduced, okay, compared to the accuracy of original OOB data. So the decrease in accuracy or increase of OOB error can be averaged over all decision trees. So that's the definition of the importance of variable, okay? So this decrease in accuracy or increase of OOB error is used as the measure of importance of a certain attribute in random forest. So as I said, the basic idea is the more the increase of OOB error is, or the more the decrease of the accuracy is, the more important is the variable. That's the basic idea of variable importance. This picture shows the example of computing variable importance in random forest. Suppose we have original data here, and there are many samples by using bagging. So we have a data set 1, and there are many here, and data set M. So we have m different sample here, and this, let's say this is OB data of data 1, and this is OB data of data m. Okay, so by using this data set 1, we build a decision tree. By using a data set m, we have a decision tree m. Okay, and by using this decision tree 1, we compute the accuracy, or you compute the error of OB, original OB data. Okay, let's say this is original error. This is error of original OB data, E1. So E1 is error of original OB data. Okay, and same thing here. By using the decision tree M, we compute the error of OB data M. So the error EM is the error of OB data M. Okay. Then you compute, you modify, okay, you modify you change the values of a certain attribute I. Okay, you permute values of attribute I. You choose a certain attribute I and randomly change it. Okay, so this OB data 1 is now modified. Okay, so by using the same decision tree, now recompute the error of this modified OB data 1. Okay, and let's say that error is P1. Okay, in a similar way, here in OB data M, you choose the same attribute I and randomly change the value of attribute I. Okay, and then by using the same decision tree M, you compute the error of this modified OB data M. Let's say that error is PM. Okay, and there is the difference between these two, and probably, okay, this error is higher than this error, because if this attribute is important, this attribute important, and then if you randomly change the value of this attribute, probably, okay, this may increase the error of method, right? So if you change the value of certain attribute I, probably this value, this error will be higher than E1. Okay. Same thing here. You change the value of attribute I, and if attribute I is important, probably this error is higher than this error, right? Because attribute I is important. So, but on the other hand, if the attribute I is not important, then you change the values of this attribute I, then probably there is not much change between these two. And same thing, if this attribute I is not important at all, but even though you change the values of attribute I, there is very little change here, okay, or little or no change here. Okay. So anyway, the D value is difference between these two, okay, and the D value here is again the difference between these two values. So the final variable importance of attribute I is the summation of these D values, okay, across all decision trees, or the average value of these D values. So summation of D values or average of D values is defined as the importance of attribute I. Okay, that's how we compute the importance of attribute in a random forest. Another interesting feature of a random forest is called proximity plots. So in proximity plots, we are able to compute the similarity between two data. That's called the proximity plots in random forest. So random forest introduces a novel way to define similarity between two data. The way it works is the following. So suppose the prox ij means the similarity between data I and data j. So in the beginning, these prox values are zeros, okay? So there are many decision trees. You pick one of them and you apply this decision tree to every data. Okay, so every data end up in the leaf node of decision tree, right? So if a certain data, two data, data I and data J end up in the same leaf node, okay, so this data I, data J, arrive at the same leaf node, class label, okay, then you increase the value of prox ij by 1, okay? That means this data I and data j arrive at the same leaf node, okay? Then you increase this value by 1. So you repeat this by using every decision tree, I'm sorry, okay? Then at the end, you the final value of prox ij is defined as the similarity between data I and data j. So idea is quite straightforward, but it's a very interesting property of random forest. So the resulting matrix, okay, of size n by n is the size of data. Okay, so we have a two-dimensional matrix, n by n. It's called proximity matrix, and it provides the intrinsic measure of proximity between data. So by using proximity plots, it is easy to compute the distance of data. Okay, distance is just opposite of similarity. So by using this proximity plots, we can use this proximity plot matrix as a method of computing distance in clustering. Okay, so you can use this method in clustering algorithm as well. And also by using these proximity plots, you can visualize the entire data, okay, in a two-dimensional or three-dimensional way. That's another advantage of using proximity plots. So you can make use of these proximity plots in many different ways. You can define the similarity between data, and you can define distance of data and use it in clustering algorithms. And you can also visualize the entire data by using proximity plots. So having the full intrinsic proximity matrix, okay, it opens new horizons, as I mentioned. So it gives you informative data views by using visualization of data. And another advantage is it is quite easy to detect some outliers in the data by using visualization. So you can see entire structure of data by using visualization. So it is quite easy to detect some outliers in the data. But there are some issues in proximity plots. If your data is too big, actually the matrix size gets out of control. Okay, so for example, if your data size is 5,000, okay, which is not very big actually, but the matrix size, the proximity matrix size is over 25 million, okay? So let's say your data is like 1 million, the size of proximity matrix is just out of hand, okay? So that is the one issue of proximity plots. So if your data is too big, actually the random forest uses a more compressed version of proximity matrix, okay, but which we do not cover here. This slide compares a random forest with a single decision tree. Random forest gives us the many benefits of decision trees, including handling missing values and handling continuous and categorical attributes. But at the same time, it still gives us better results than single decision trees. So that these are the advantage of random forest. And another advantage is in random forest, we do not need tree pruning. Okay, that's another advantage. This makes actually a random forest much faster than a decision tree. And also, even though there is no pruning process, a random forest improves the accuracy compared to a single decision tree. This table shows the accuracy between random forest and single decision tree. Actually, these are errors. So for every data here, the random forest consistently shows lower error rate compared to a single decision tree. So random forest provides many benefits, many advantages, but still it gives us much more higher accuracy than a single decision tree. So some final remarks on random forest. The first one is random forest shows much better performance than a large single decision tree. That's first advantage. And random forest can handle hundreds or even thousands of attributes. In random forest, when you construct a decision tree, it doesn't consider entire attribute. It select a small subset of attribute first, okay, and then you select one node out of this small set, okay. So that way, it can handle hundreds or even thousands of attributes. And there are some randomization element in random forest, okay, and it makes this algorithm very resistant to overfitting. There are two randomization elements in random forest. The first one is bagging. So in bagging, you randomly select data. That is the first randomization element. And second randomization element is when you construct decision tree, you randomly select attribute out of the entire attribute, right? That's the second randomization element. So by using these two randomization element, actually it makes this decision random forest decision trees quite independent to each other. So again, as I said many times, in ensemble method, one of the most important thing is to maintain the independency between each classifiers. Okay, so in random forest, by using these two randomization element, okay, it maintains the quite enough sufficient level of independency between these decision trees. And random forest can be applied to regression and the classification model. That's another advantage. In machine learning, the test error is much more important than training error. And in random forest, the OOB data plays the role of test data. So by computing the OOB error, we can estimate the size of test error of the method. That's a big advantage of using random forest. So we can estimate the test error of random forest by using OOB error. So this generates an internal unbiased estimate of the test error. So because we can estimate test error by using OOB error, we don't need a cross validation process in random forest. So that's another advantage. And as we have seen in proximity plots, we can estimate the similarity of samples. And also feature importance can be computed during training. We have seen this in variable importance. And actually, this random forest is quite faster to train. It generates multiple decision trees, but it doesn't do pruning process there. So because of that, random forest is quite faster to train. And the random forest has just a few parameters, such as the number of decision trees and the number of attributes you're going to choose when generating decision trees. And finally, the random forest, its performance is quite competitive, okay? And it has pretty much the same accuracy with SVM or a neural network. So even though the algorithm is quite simple and easy to implement, its performance is quite competitive with some other more advanced algorithm like SVM or neural network.